Good morning. Good morning to everybody. Myself Balwinder Singh, HOD Mechanical from GP Batala. Today our topic is, it is related with the thermal engineering, Otto cycle, diesel cycle, dual cycle. Before entering to this cycle, we must know what is thermodynamic cycle. Before entering to Otto cycle, diesel cycle, dual cycle, we must know what should be the thermodynamic cycle. Let us have a graph PV, pressure, volume. Now, I will draw first point, second point, third point, fourth point, and then again first point. So, thermodynamic cycle is concerned with a number of processes, that is 1 to 2 one process, 2 to 3 another process, 3 to 4 another process, 4 to 1 another process. So, that means cycle is a combination of the processes in which the working fluid works in this cycle and return to original position, that is first point. Then we called it a thermodynamic cycle. Cycle is said to be occur when the working fluid changes its position from 1 to 2 by doing some process, then again return to its original position, that we say cycle is occur. Now, this is the thermodynamic cycle. The process may be adiabatic, may be isothermal, may be isochoric, may be isobaric. Adiabatic is process in which the heat is constant, whereas in isothermal temperature is constant, isochoric volume is constant, isobaric pressure is constant. Now, these all are processes which may occur in a cycle. So, this is a thermodynamic cycle. Now, different engine works in different cycles. Now, we will discuss what is Otto cycle. Otto cycle, as its name indicates, it is invented by German scientist Otto in 1878. It is also called petrol cycle. Now, I will show it on the PV diagram. Take pressure on one side, volume on one side, this is your first point, second point, third point, fourth point. Otto cycle is also a constant volume cycle. Now, 1 to 2 process, we called it a adiabatic, reversible adiabatic process or isentropic process. 2 to 3 constant volume process, and 3 to 4 adiabatic reversible process, and 4 to 1 is constant volume process. Now, this Otto cycle works on constant volume. Now, during first to second point, it is a adiabatic compression process. Now, at first point, fuel is entering the cylinder. If I will draw a diagram on this, let us say this one is your cylinder and this is your piston. This is the position of the piston in which all the fuel is taken into the cylinder. That point is plotted on the graph, that is first point. Let us say at this point the pressure is P1, V1, T1. Then this piston moves to the top dead center, that is from 1 to 2 compression is taken place and second point is plotted here. As you know, the compression is there, that means the pressure changes, volume changes, temperature changes. Again 2 to 3 process at this point, the heat is added into the cylinder at constant volume. That means here the volume remain constant, pressure changes, temperature changes, and again expansion process is taking place, that is 3 to 4 process, that is isentropic expansion of the cycle, and the work is done on the piston. The piston moves to and fro motion. So, how the cycle takes place during Otto cycle. Now, these are the different positions of the Otto cycle. Now, we will find out what should be the work done. Now, let us find out the work done in this case. Now, work done is what? Work done is heat supplied minus heat rejected. Heat supplied, that means 2-3 process in which heat is added. We know the formula, if 1 kg is the gas, then we say specific heat at constant volume is Cv, change in the temperature, that is T3 minus T2. What is the heat rejected during exhaust stroke? 4 to 1. Specific heat at constant volume, the change in the temperature T4 minus T1. So, this is our work done. Work done is nothing but the heat supplied minus heat rejected. Now, we will find out the air standard efficiency of the cycle, which is equal to the work done divided by heat supplied. Now, what should be the work done? We have found out Cv T3 minus T2 minus Cv T4 minus T1. This is the work done, and the what is the heat supplied? Same Cv T3 minus T2. This is our efficiency. We will further derivate it. Efficiency I will write on this, that is Cv T3 minus T2 minus Cv T4 minus T1 divided by CV T3 minus T2. It can be further derivated 1 minus T4 minus T1 divided by T3 minus T2. We know compression ratio, we want to know what should be the efficiency of the Otto cycle in terms of the compression ratio, which is very important. Compression ratio means volume of the cylinder divided by clearance volume, which is denoted by R. Now, this is the total cylinder volume, that is the swept volume and clearance volume. This is the clearance volume. If I will show you the graph, this is the clearance volume, and from this point to this point, this is the cylinder volume. Now, we will find out the efficiency in terms of the compression ratio. Now, take process 1 2. 1 2 means this one. Apply one standard formula I will show for you. Always remember T2 by T1 is equal to V1 divided by V2 gamma minus 1. This is further equal to P2 by P1 gamma minus 1 divided by gamma. This is a standard gas equation. From this formula you can derive, you can find out the further relations. Now, I will take this one. Now, during the process 1 2, what is T2 by T1 is R gamma minus 1. Compression ratio, we have taken V1 divided by V2 is compression ratio of the cylinder. So, second T1 is nothing but R gamma minus 1 divided by T1 is T2 by R gamma minus 1. Now, take second process, that is 3-4 expansion process. In this case, again apply the same formula, T3 divided by T4 is what? V4 divided by V3 gamma minus 1. V4 and V3, this is again a compression ratio R, because we are working, the cycle is working on constant volume process. So, we can write it R gamma minus 1. Now, again you find out what is T4 here, T3 divided by R gamma minus 1. Put this value in this equation, that is A equation. We will further derivate efficiency is equal to T4 is T3 divided by R gamma minus 1 and T1 is T2 R gamma minus 1 divided by T3 minus T2. Now, this is further equal to 1 minus R gamma minus 1 T3 minus T2 which is cancelled out. So, efficiency is nothing but in terms of the compression ratio R gamma minus 1. Now, here gamma is nothing but the ratio of the specific heat at constant pressure divided by specific heat at constant volume. It is generally equal to 1.4, the value may be varied. Now, this is the relation air standard efficiency of Otto cycle. From this formula, you can calculate the numericals. If the compression ratio is given, you put the value here, you can find out the efficiency. If the gamma is given, you can find out the efficiency. If the examiner say find out the work done, you can find out the work done, what is heat supplied minus heat rejected. Now, this is if we plot a graph on this efficiency and compression ratio, what you get is, let us say this is your compression ratio, okay, and this is your efficiency. You will see as the compression ratio increase, then what will happen? Efficiency increase, and the graph is like this. So, that means as the compression ratio increases, second factor decreases and the efficiency increases. This is the relation between the efficiency and compression ratio on the graph. Now, this is your Otto cycle. Now, I will go to the second cycle, that is diesel cycle. Now, diesel cycle is also called, as the name indicates, it is invented by the diesel scientist. Now, if we plot it on the graph, that is pressure volume graph, first point in which the fuel or air is enter into the cylinder, then compression takes place. Now, the heat is added at constant pressure. The difference is, in this case, this is also constant pressure cycle. The heat is added at constant pressure, whereas the heat is rejected at constant volume. So, I will show for you 1-2 process is isentropic process, isentropic or reversible adiabatic process, in which the compression is take place. This one is the compression process. We know here the value P1, V1, T1 during compression, when the piston moves to the top dead center at point 2, the value of the pressure raises P2, V2, T2, and the process is isentropic. Now, the heat is added as the air is compressed in the cylinder, then what will happen? Temperature raises, you add the fuel there, that is diesel fuel. That fuel is entered in constant pressure process. So, 2-3 process is constant pressure process, in which the heat is added, heat added. When the heat is added, then expansion takes place. The gases expands in the cylinder. What will happen? From 3 to 4, expansion take place. So, 3 4 is isentropic or reversible adiabatic process expansion, and 4 to 1 again the cycle is completed, and the 4 to 1 exhaust gases are rejected, heat is rejected, heat rejected. So, these are the different processes which take place during the diesel cycle. Now, in the same way as we have done in the Otto cycle, we will find out what should be the work done here. Work done again, heat supplied minus heat rejected. Now, what is the heat supplied? This is the process 2 3. So, we will write here, now the specific heat is at constant pressure C p, and the change in the temperature is T 3 minus T 2, and minus heat rejected. What is the heat rejected here? 4 1 process, which is at constant volume. That means, you have to take specific heat at constant volume, and temperature difference is T 4 minus T 1. So, this is the work done. Again you find out what should be the efficiency. Efficiency is what? Efficiency is C p T 3 minus T 2 minus C v T 4 minus T 1 divided by heat supplied C p T 3 minus T 2. So, this is the efficiency. It can be further written like this: 1 minus C v divided by C p T 4 minus T 1 divided by T 3 minus T 2. C p over C v is nothing but gamma. So, we can write 1 minus 1 by gamma T 4 minus T 1 divided by T 3 minus T 2. Here we can further derivate this relation in terms of the compression ratio. Again, there is one term used here is cut off ratio, which is denoted by a rho, which is equal to V 3 divided by V 2. Compression ratio R is nothing but V 1 divided by V 2. Now, V 4, if you divide V 4 divided by V 3, we can write it V 4 divided by V 2 and V 3 divided by V 2. We have divided V 4 by V 2, V 3 by V 2. What is this? This is compression ratio R. V 3 by V 2, I have explained you, this is known as cutoff ratio. So, we can say V 4 by V 3 is nothing but compression ratio divided by cutoff ratio. So, we can further derivate it. We can write efficiency efficiency equal to 1 minus 1 by gamma T4 minus T1 divided by T3 minus T2. Now, take the first process. One to two process. I will again show here the graph. This is T2 minus divided by T1 is equal to V1 divided by V2 gamma minus 1, which is R gamma minus 1. Now, this is our first relation, then take 2, 3 process. T1 is T2 divided by R gamma minus 1, and 2, 3 process we take it as it is constant pressure process. We apply here gas equation P2 V2 divided by T2 is equal to P3 V3 divided by T3. This is not a isentropic process. Generally, this formula is applicable in case of adiabatic isentropic process, whereas in case of 2-3 process we can apply this formula, that is gas equation. So, pressure is constant here, we can write it like this V2 divided by T2 is equal to V3 T3, or T2 is nothing but V2 divided by V3 multiplied by T3. What is V2 by V3? I have shown you that V3 divided by V2 is cut-off ratio, this is equal to 1 by rho V3, which is T3. Now, this is our second relation, this is our first relation. Now, put the value of T2 in case of T1, and T1 is equal to T3 rho R gamma minus 1. This is your third relation. Now, take 3-4 process. Take 3-4 process. Again apply the same formula I have shown you. T3 divided by T4 is V4 divided by V3 R gamma minus 1. V4 by V3 is nothing but R divided by rho gamma minus 1. So, T4 here is T4 is what T3 divided by R rho gamma minus 1. T4 is taken in inside in this side, and this term is divided by T3. So, this is our fourth relation. Now, put this value, that is 2, 3 and 4 in equation number A. What you get is efficiency is equal to 1 minus 1 by gamma.